For hundreds of millions of years, Earth's continents have drifted, collided, and broken apart. Again and again, they have assembled into giant supercontinents, roughly every 300 to 500 million years, following a deep tectonic rhythm linked to slow mantle convection far beneath the crust. Today, we explore how this supercontinent cycle works, why it repeats, and what it reveals about Earth's distant past and far future. If you enjoy calm journeys into deep time, please like, subscribe, and share, and tell us in the comments what would you most like to ask about Earth's next possible supercontinent. Thank you for watching. Now let's begin. Earth is a rocky planet that operates as a tectonic system. In scientific models, it forms about 4.5 billion years ago from material in the young solar system, and since that time its interior stays hot enough to keep large parts of the deep mantle slowly flowing. The planet has a radius of a little over 6,000 kilometers, so the distance from the surface to the center is large, and pressure and temperature increase steadily with depth. Near the center there is a metallic core outside that a thick silicate mantle, and at the surface a thin solid crust. The mechanical behavior of these layers is not uniform. In the upper part of the mantle, together with the crust, a relatively cool and rigid shell exists. This shell is called the lithosphere. Beneath it, higher temperatures and pressures allow the mantle to deform more easily over long time scales. This region is called the asthenosphere. The contrast between a strong lithosphere and a weaker underlying asthenosphere allows the outer shell to break into separate pieces and to move as plates. In plate tectonic theory, the lithosphere is divided into several large plates, and many smaller ones, each carrying ocean basins, continents, or both. These plates move very slowly over the softer asthenosphere, at rates of at most a few centimeters in 1 year, comparable to the speed at which fingernails grow. The motions are measurable with modern satellite geodesy and are consistent with geological evidence recorded over tens of millions of years. At the edges of plates, relative motion concentrates deformation into narrow or sometimes broad boundary zones. Along some boundaries, plates move apart and new lithosphere forms from upwelling mantle. Along others, plates converge so that one plate sinks back into the mantle, or two continental regions collide and thicken. Along yet others, plates slide past one another laterally. These plate boundaries localize earthquakes, many volcanoes, and major mountain belts, while the interiors of plates are comparatively stable on human timescales. This pattern means that the surface of Earth is not a static outer shell, but a mobile system of rigid blocks moving on a slowly flowing interior. The energy that sustains this system comes from internal heat. Part of that heat is left over from the planet's accretion and early differentiation, and part comes from the decay of long-lived radioactive isotopes in mantle and crustal rocks. Heat escapes toward the surface through conduction in the lithosphere and through slow convection in the deeper mantle. Where hot material rises, it can thin and weaken the lithosphere. Where cold, dense lithosphere sinks, it draws plates along. The result is that plates continually form move and are recycled into the deep mantle over hundreds of millions of years. Because plates carry continents on their upper surface, the positions of continents relative to one another change steadily through time. Ocean basins open where lithosphere is created and close where it is consumed. In this framework, continents are not fixed reference features, but parts of moving plates that can separate, converge, and sometimes join with other continents. Geological evidence from many regions shows that continental crust is generally older and less dense than oceanic crust, that it resists subduction, and that fragments of it can survive many cycles of plate interaction. As a result, Earth at any given time presents a particular distribution of continents and oceans that reflects the integrated effect of plate motions, over previous tens to hundreds of millions of years. The preservation of old continental cores called cratons within younger belts of deformed rocks and mountain ranges records past episodes of collision and rifting. In the oceans, the age of the crust and the pattern of magnetic stripes on the seafloor record, spreading at mid-ocean ridges and the creation of new lithosphere. Together, these observations support the view that Earth is a tectonic planet whose outer shell is continuously reshaped by plate motions driven by internal heat loss. The theory of plate tectonics provides a quantitative framework in which present-day motion's seismic activity and the global pattern of ocean basins and continents can be described in a consistent way. Within this framework, the surface of the planet is recognized as dynamic on geological timescales, with continents that drift on moving plates and with ocean basins that are created and destroyed over many tens or hundreds of millions of years. At the scale of human lifetimes, this motion is extremely slow, but over the full span of Earth history it results in repeated large-scale reorganizations of the entire surface. In this way, the current arrangement of land and sea is one stage in a long sequence, controlled by the tectonic behavior of the lithosphere above a convecting mantle. Earth history is described using a geological timescale that spans from the earliest preserved crust to the present day, and divides this long interval into large named units based on changes in rocks, fossils, and global conditions. The total duration involved is more than 4 billion years, so long that even very slow processes have time to produce large effects on the shape of continents and oceans. To handle this range, stratigraphers define eons, eras, periods, and finer units that mark boundaries where rock successions, fossil assemblages, or geochemical indicators change in a consistent way. Within these divisions, plate tectonics provides a physical mechanism that operates through much of Earth history, with plates moving at speeds of at most a few centimeters in 1 year and maintaining broadly similar directions for many tens or hundreds of millions of years at a time. Present-day plate motions measured with geodetic methods show that individual plates shift laterally across the surface, and geological records from older rocks indicate that comparable motions occur in many past intervals. When this slow displacement is integrated over tens of millions of years, continents attached to plates do not remain in fixed positions. They drift across low and high latitudes, move toward or away from the poles, separate from neighboring land masses as rifts open, or approach one another along convergent margins. Over longer spans of hundreds of millions of years, these motions generate large reorganizations of the pattern of land and sea. Areas that are now widely separated can once have been neighbors along the same plate boundary, while regions that are now adjacent can previously have had long independent histories as parts of different plates. In deep time, the positions of continents relative to the equator and the poles and relative to one another change repeatedly as plates follow different paths on the spherical surface of the planet. The geological timescale allows these changes to be placed in order by assigning ages to rocks and structures formed during different episodes of plate interaction, so that reconstructions of past continental configurations can be tied to specific intervals. Early work on continental drift relies on large-scale observations, such as the matching outlines of continental shelves on either side of the Atlantic and other oceans, and the distribution of similar rock sequences and land-dwelling fossils on land masses that are now separated by broad ocean basins. Later developments in plate tectonic theory add information from the oceans, including the pattern of ages in the oceanic crust, the symmetry of magnetic anomalies about mid-ocean ridges, and the alignment of volcanic island chains and deep ocean trenches. These observations together indicate that ocean basins are not permanent features. New oceanic lithosphere forms at mid-ocean ridges, moves away from them, as it cools and thickens and eventually returns to the deep mantle at subduction zones. Because oceanic plates carry continents on their upper surface, the opening and closing of ocean basins as recorded in the geological timescale naturally produces changes in the spacing and arrangement of continents. A continent that lies near a spreading ridge in one interval can be carried toward a subduction zone, in a later interval changing its neighbours and the configuration of surrounding seas. When several plates are considered together over long spans of time, their combined motions redistribute continental fragments across the globe. Some pieces remain attached and travel together for long intervals, forming composite landmasses that persist through several geological periods. Other pieces split away along rifts that cut older crust and create new plate boundaries that guide later motion. The timing of these events is estimated by dating igneous rocks formed during rifting and collision, and by relating these ages to the global timescale, so that episodes of separation and convergence can be assigned approximate durations. As the geological timescale is refined, the resolution with which these stages of motion can be distinguished improves, allowing differences of many tens of millions of years in the timing of plate interactions to be recognized. This refinement permits reconstructions from different regions to be compared and tested for consistency with multiple kinds of observation. Across Earth history, episodes of widespread mountain building development of broad continental shelves and formation of large interior basins appear in many rock records and often coincide with major changes in plate interactions. With the geological timescale in place, these long intervals can be associated with particular patterns of plate motion, such as extended periods of convergence between major plates or long phases dominated by rifting and seafloor spreading, so that the cumulative effects of plate motion on the distribution of continents and oceans through deep time can be followed in a coherent sequence. In plate tectonic theory, a supercontinent is defined as a landmass that combines most of Earth's continental lithosphere into a single connected region, so that only minor continental fragments, island arcs and microplates remain outside the main assembly. Geological and geophysical studies indicate that such large groupings do not occur only once in Earth history, but appear several times separated by long intervals in which continents are dispersed in multiple clusters. To describe this long-term behavior, geologists use the term supercontinent cycle. In this context, the supercontinent cycle is the quasi-periodic sequence in which continents move from a dispersed state through progressive collisions into a configuration that approaches a single large landmass, remain in that assembled condition for a significant interval, and then enter a phase of renewed rifting and dispersal. The cycle is inferred from the timing of major orogenic belts, large-scale sutures between continental blocks and other markers of continent-continent collision, as well as from paleomagnetic and geological reconstructions that place large numbers of continental fragments together at particular times. When these data are ordered on the geological timescale, episodes of near-global continental aggregation appear at several widely separated ages. Estimates based on these reconstructions and on numerical models of mantle convection and plate motion indicate that one complete supercontinent cycle from assembly through maximum dispersal to the next assembly typically requires on the order of several 100 million years. Many reviews cite a characteristic range of roughly 300 to 500 million years for a full cycle, while acknowledging that individual intervals may lie outside this range, depending on how assembly and breakup are defined, and which reconstructions are adopted. Within a single supercontinent cycle, different stages can be distinguished. During the assembly stage, long-lived subduction zones consume large ocean basins between wandering continents and major collisional origins develop where buoyant continental blocks converge. As assembly proceeds, the number of large continents decreases, and the remaining land masses become integrated into a contiguous or nearly contiguous unit. In a following stage, the supercontinent persists while internal stresses thermal insulation of the mantle beneath the large landmass, and changes in convection gradually modify the pattern of plate boundaries around and within it. Later, a breakup stage begins in which rifts form within the supercontinent, new plate boundaries develop, and nascent ocean basins open between fragments that drift apart on newly formed plates. A final dispersal stage is reached when the former supercontinent has been subdivided into several major continental groups, separated by wide oceans, so that the proportion of continental crust in one connected region is again low. This long-scale pattern is distinct from but related to the Wilson cycle. The Wilson cycle describes the opening and closing of individual ocean basins along specific plate boundaries, from initial rifting to mature oceanic spreading subduction and eventual closure. Wilson cycles operate on parts of the plate system and typically involve timescales of a few 100 million years or less for one ocean domain. The supercontinent cycle, in contrast, tracks the combined effect of multiple overlapping Wilson cycles, acting on many plates over longer intervals, and it concerns the configuration of nearly all continental crust at the planetary scale, rather than the life history of a single ocean basin. Because both concepts are built on the same underlying plate motions, their timescales can overlap, but they address different levels of organization in the tectonic system. In this framework, the supercontinent cycle is defined as the repeated large-scale aggregation and dispersal of almost all continental crust over intervals of several 100 million years, while the Wilson cycle refers to the opening and closing of individual ocean basins within that broader pattern. Pangaea is reconstructed as the most recent supercontinent in Earth history, assembled from earlier continental groupings during the late Paleozoic and beginning to fragment during the early Mesozoic. In these reconstructions, most of the present-day continents are joined into a single landmass that is nearly surrounded by a global ocean known as Panthalassa, while smaller ocean basins such as the Paleotethys and later the Tethys occupy positions along its margins. The combined landmass extends from high southern to high northern latitudes and has an overall curved outline with a broad interior and long arms that wrap around interior seas. Continental crust that now belongs to Africa, South America, North America, Europe, Asia, India, Australia and Antarctica is placed in contact within this single configuration, with sutures and mountain belts marking former collision zones between once separate plates. Geological and geophysical evidence indicates that assembly begins roughly in the late Carboniferous period, when large continental blocks that have previously moved independently start to converge. One major component is Gondwana, a southern high-latitude landmass composed of what will become Africa, South America, India, Australia, Antarctica, and several smaller regions. To the north, Laurussia or Euramerica containing crust that will later form parts of North America and Europe lies on another plate system. Progressive subduction of intervening oceanic lithosphere brings these units together along a series of collisional origins. The closure of the Rhaetic Ocean and related basins joins Laurussia to Gondwana along a belt that later includes the Appalachian Variscan and related mountain systems. These belts are interpreted as traces of the zones where continental margins once faced open oceans and then collided, and their present distribution across multiple modern continents is consistent with a former continuous chain. Farther east collision between Siberia and Kazakhstania with the growing composite mass closes other ocean domains and helps to form the Uralian belt, which today links regions of Eastern Europe and Western Siberia. As these collisions proceed, the number of large independent continents decreases, and by early Permian time, most continental crust is incorporated into a single connected landmass. The timing of full assembly is constrained by radiometric ages of magmatic and metamorphic rocks in these orogenic belts, by stratigraphic relationships in adjacent basins, and by paleomagnetic data that place continental blocks at compatible latitudes and orientations. These data sets together support a reconstruction in which Pangaea is effectively assembled by early Permian time, after a protracted sequence of collisions that spans tens of millions of years. Once in place, the supercontinent persists through the remainder of the Permian and into the Triassic period. During this interval, its margins are defined by long subduction zones, where oceanic plates of Panthalassa and other basins descend beneath the continental edges, while its interior is largely preserved from new plate boundary formation. The arrangement of land and sea during this time is recorded in sedimentary basins, volcanic sequences and paleomagnetic poles that can be assigned to specific parts of the supercontinent. Reconstructions indicate that the interior includes large continental plateaus, broad low-lying basins and high mountain ranges inherited from earlier collisions, while long coastal regions face Panthalassa and peripheral seas. Breakup of Pangaea begins when new zones of extension develop within the interior and along some margins. In late Triassic to early Jurassic time, rifting initiates in regions that will later separate into distinct continents. Normal faulting dike swarms and thick accumulations of continental volcanic rocks and sediments mark these early rift systems. One important rift network develops between what will become North America and northwestern Africa and Europe, and another affects regions that will later form parts of Gondwana. Additional rifting occurs in areas that are now within East Africa, Antarctica, and regions of the southern Atlantic and Indian Ocean margins, indicating that extension is not confined to one narrow corridor, but affects several parts of the supercontinent. As extension continues, some rifts progress to full seafloor, spreading and narrow ocean basins of newly formed oceanic crust appear between continental fragments. With continued opening, these young oceans widen and connect, while the former interior of the supercontinent becomes divided into separate plates. In many reconstructions, Pangaea first splits into a northern continent, commonly called Laurasia, and a southern continent commonly called Gondwana. Laurasia includes crust that will become North America, Europe, and much of Asia, while Gondwana contains the future Africa, South America, India, Australia, and Antarctica. The separation between these units is associated with the initial opening of what will develop into parts of the Central Atlantic Ocean and later related basins. Over the following tens of millions of years, further rifting within these large continents leads to additional fragmentation. South America and Africa begin to move apart, opening the South Atlantic. India eventually rifts away from eastern Gondwana and migrates northward on its own plate. Australia and Antarctica separate at later stages. Throughout this breakup sequence, the positions and shapes of ocean basins and continental margins recorded in marine magnetic anomalies, fracture zone trends, and passive margin stratigraphy constrain the kinematics of plate motion. By Middle Jurassic time, Pangaea no longer forms a continuous supercontinent, and the continental fragments produced by its breakup occupy distinct positions separated by young ocean basins. Gondwana is reconstructed as a large southern high-latitude landmass that brings together many of the continental blocks that now form South America, Africa, India, Australia, Antarctica, Madagascar, and several smaller regions. In most models of the supercontinent sequence, Gondwana exists as a coherent assembly before the final construction of Pangaea, and then continues as the southern component of Pangaea once collision with northern continents is complete. Its history extends over a long interval that begins after the breakup of the older supercontinent Rodinia and runs through much of the late Neoproterozoic and early Paleozoic, with many reconstructions placing the main phase of assembly between about 600 and 500 million years ago. Geological syntheses describe Gondwana as forming through the fusion of several ancient cratons and continental blocks during a series of orogenic events that include what is widely grouped under the term Pan-African orogeny. In this interpretation, multiple ocean basins that once separated these cratons close along long belts of deformation, metamorphism, and magmatism that today can be traced across large parts of Africa, South America, Antarctica, India, and Australia. These belts preserve evidence for high-grade metamorphic conditions, large-scale thrusting and widespread plutonism, all features characteristic of continent-continent collision. The present distribution of these belts on now distant continents is used to reconstruct former sutures where previously separate blocks joined, and radiometric ages from these rocks constrain the timing of collisions that contribute to the amalgamation of Gondwana. Paleomagnetic data from Neoproterozoic and early Paleozoic rocks in several of these regions provide estimates of paleolatitude and help to test whether proposed configurations produce consistent positions for each block at given times. Many studies indicate that by early Cambrian time most of the major cratons that will later make up Gondwana lie adjacent to one another along these sutures, forming a continuous southern hemisphere landmass that extends from near the South Pole toward lower latitudes. Some reconstructions treat Gondwana during this stage as an independent supercontinent or superterrane that contains a large proportion of Earth's continental crust, particularly in the southern hemisphere. Within this framework, Gondwana persists in a relatively coherent form from late Neoproterozoic time through much of the Paleozoic, with internal deformation and magmatic activity in some regions, but without wholesale dismemberment into widely separated continents until later stages. During the Ordovician, Silurian, Devonian, and Carboniferous periods, the margins of Gondwana host long subduction zones, where oceanic lithosphere of surrounding basins descends beneath the continental edge. These convergent margins give rise to extensive magmatic arcs and accretionary complexes now preserved, for example, along parts of the Andes in sectors of eastern Australia and in parts of Antarctica and India. On other segments of the margin, long-lived passive margins develop where continental crust faces widening ocean basins and accumulates thick sedimentary wedges on broad continental shelves. Within the interior of Gondwana, earlier orogenic belts and cratonic cores form a mosaic of relatively stable blocks, and older mountain systems and large sedimentary basins collect material eroded from these highlands. Glacial deposits of late Paleozoic age found on several now separated continents, including southern Africa, South America, Antarctica, India, and Australia, are interpreted as evidence that large parts of the Gondwanan interior lie at high southern latitudes during these intervals, reinforcing the view that these regions were once joined. Fossil assemblages and stratigraphic successions found across different Gondwanan fragments also support their former connection by showing closely related floras and faunas and similar sedimentary histories across areas that are now separated by oceans. As plate motions proceed through the Paleozoic, Gondwana approaches and eventually collides with continental blocks to the north, including Laurussia and other units. These collisions contribute to the formation of Pangaea and generate additional orogenic belts along what will become the sutures between Gondwana and the northern continents. In many reconstructions, Gondwana during this phase behaves largely as a single entity, moving as a composite plate or group of plates with limited internal separation, so that it effectively acts as the southern half of the Pangaean supercontinent once full collision is achieved. The time span over which Gondwana remains a coherent southern landmass is estimated in several models to run from about late Neoproterozoic time until roughly early to middle Carboniferous time as an independent superterrane, with its later history tied into the combined evolution of Pangaea. The eventual breakup of Gondwana into the continental fragments that will become the modern southern continents begins much later during the Mesozoic, and involves new rifting and ocean opening that lie beyond the interval of assembly and long-lived coherence considered in this part of the supercontinent sequence. Pangaea is described as a short-lived late Neoproterozoic supercontinent that forms after the breakup of Rodinia and before the long-lived assembly of Gondwana and Pangaea, though its exact configuration and even its status as a distinct supercontinent remain under active discussion. In many reconstructions, Pangaea exists for only a few tens of millions of years, near the transition between the Ediacaran period and the early Cambrian, roughly between about 600 and about 550 million years ago, and consists of a large grouping in which the main blocks that will later become Gondwana lie adjacent to Laurentia Baltica and Siberia in a mostly high-latitude arrangement. In this view, continental crust that now resides in Africa, South America, India, Australia, Antarctica, and several other cratons is already fused into a southern composite mass, and additional collisions bring Laurentia Baltica and related blocks into contact along sutures that close earlier ocean basins. Some models place much of this aggregate landmass around the South Pole, with broad continental shelves and passive margins facing a surrounding ocean, and with long internal orogenic belts marking the sites of late Neoproterozoic collisions. The geological framework for Pangaea is tied to a series of orogenic systems that record the final stages of Rodinia breakup and the early stages of Gondwana assembly. These include the Pan-African orogeny in Africa and surrounding regions, the Brasiliano belts in South America, the East African, and Kunga orogens linking parts of East Africa, Madagascar, India and Antarctica, and related collisional zones in Arabia and other blocks. Rocks in these belts typically preserve evidence of high-grade metamorphism, large-scale thrust faulting crustal thickening, and widespread granitoid magmatism that occur between about 700 and about 550 million years ago, and are interpreted as the products of ocean basin closure and continental collision. In some reconstructions, when these belts are restored to pre-breakup positions, they outline a nearly continuous network of sutures, joining most of the major cratons into a single connected landmass, which is taken as support for the existence of a late Neoproterozoic supercontinent. Paleomagnetic poles obtained from Neoproterozoic and earliest Cambrian rocks on several cratons provide additional constraints on latitude and orientation. Some compilations of these data allow fits in which Laurentia Baltica and Siberia lie along the rim of a larger composite landmass that includes the core Gondwanan cratons, in positions consistent with the inferred collision belts. Other polarity paths and age assignments permit alternative relative positions that do not require such a unified configuration. As a result, Pangaea is often reconstructed with broader uncertainty envelopes than younger supercontinents such as Pangaea, and published maps for this interval differ in the precise arrangement of blocks, even when they agree on the general timing of major collisions. The breakup of Pangaea is associated in many studies with the development of new rift systems and passive margins that herald the opening of the Iapetus Ocean and other early Paleozoic basins. In these scenarios, after a brief interval of near-global aggregation extension, develops along several internal zones and margin segments of the composite landmass. Normal faulting dike swarms and the onset of new sedimentary basins record stretching of the lithosphere, where rifting progresses to full seafloor, spreading oceanic crust forms and separates Laurentia from Baltica and from parts of Gondwana, generating the branches of the Iapetus and related oceans that remain active into Ordovician time. At the same time, further internal reconfiguration among the southern cratons contributes to the final consolidation of Gondwana as a largely self-contained southern supercontinent. In this framework, the lifetime of Pangaea as a single coherent landmass is short-bounded by the final collisions that close late Neoproterozoic oceans and by the onset of new rifting that initiates early Paleozoic ocean basins. Some authors therefore emphasize Pangaea as a transient supercontinent whose assembly marks the end of one long supercontinent cycle, while its rapid breakup marks the beginning of the next, whereas others prefer to describe this interval as a prolonged transition between Rodinia breakup and Gondwana assembly, without recognizing a distinct, fully integrated supercontinent state. Independent of terminology, most studies agree that late Neoproterozoic time records widespread collisional orogenesis on many cratons' large-scale reorganization of plate boundaries and the establishment of new passive margins that define the starting conditions for the Paleozoic evolution of continents and oceans. The rocks and structures that record these events provide the main observational basis for testing competing reconstructions of continental positions during the proposed Pangaea interval, and for constraining the sequence of assembly and dispersal that links Rodinia, Gondwana, and the later supercontinent Pangaea. Rodinia is a Mesoproterozoic and Neoproterozoic supercontinent that in many reconstructions assembles from earlier continental fragments between about 1,200 and about 900 million years ago, and then breaks apart between roughly 750 and about 630 million years ago. Geological and geophysical studies identify Rodinia as a configuration in which the craton that will later form the core of North America, known as Laurentia, occupies a central position, surrounded by numerous other cratons and blocks that today make up parts of South America, Europe, Africa, Asia, and Antarctica. In a widely cited family of models, Laurentia is bordered on different margins by cratons that later belonged to Amazonia, West Africa, Baltica, Siberia, Australia, India, South China, and East Antarctica, with collisional orogenic belts marking the sutures where these blocks join. The assembly history of Rodinia is inferred primarily from the distribution and ages of these origins, many of which cluster in the interval from about 1,100 to about 900 million years ago. Examples include the Grenville origin in Laurentia, broadly contemporaneous belts in Amazonia and West Africa, and analogous late Mesoproterozoic to early Neoproterozoic collisional systems on other cratons. These belts record high-grade metamorphism, crustal thickening, and extensive magmatism, and their present positions provide clues to which cratons were once adjacent. When these origins are traced across now distant continents and restored to plausible pre-breakup positions, they outline contact relationships consistent with a single large supercontinent centered on Laurentia during early Neoproterozoic time. Paleomagnetic data from igneous and sedimentary rocks of appropriate age offer additional constraints on the positions and orientations of cratons during Rodinia time. Measurements of remanent magnetization in these rocks record past directions of Earth's magnetic field, which under the assumption of an approximately axial dipole can be used to estimate paleolatitudes. Compilations of paleomagnetic poles from Laurentia, Australia, South China Baltica, and other blocks have been used to test whether proposed configurations place each craton at latitudes and with relative rotations compatible with the observed data. Some reconstruction schemes achieve broad consistency with these constraints by placing several cratons tightly against particular Laurentian margins, for example positioning Australia and East Antarctica against the present western edge of Laurentia, or arranging Amazonia and West Africa along a different side. Other schemes invoke alternative pairings and relative rotations to fit available data. Because paleomagnetic data sets for this age range are still incomplete, and sometimes yield conflicting solutions, multiple Rodinia models remain viable, differing in details of which cratons lie adjacent and how long particular contact relationships persist. Despite these uncertainties, most studies agree that by about 900 million years ago, a large proportion of Earth's continental crust is aggregated into a single or nearly single landmass that can reasonably be described as a supercontinent. The longevity of Rodinia in this aggregated state is another topic of active research. Some models, especially earlier ones, envisage a supercontinent that remains relatively stable for about 200 million years or more, whereas others propose more rapid internal reconfiguration with significant relative motion between major sectors while broad aggregation is maintained. The breakup history is constrained by evidence for rifting and for the onset of new passive margins and ocean basins in late Neoproterozoic time. Dike swarms, rift-related volcanic rocks, and thick successions of continental to shallow marine sediments deposited in fault-bounded basins indicate that extension affects several Rodinian margins between about 780 and about 700 million years ago. These features appear, for example, along the present western and eastern margins of Laurentia, and on conjugate margins now preserved in Australia, Antarctica, and South China. As rifting continues, some of these zones progress to the formation of new oceanic crust and young ocean basins open between continental fragments that begin to move apart. Paleomagnetic paths and stratigraphic records suggest that by about 750 million years ago, Rodinia is no longer a single coherent landmass, but has begun to separate into multiple large continental groups. The fragments produced by this breakup later participate in the formation of younger, late Neoproterozoic and early Paleozoic configurations, including the proposed Pangaea and the more securely reconstructed Gondwana. In this sequence, Rodinia functions as an early Neoproterozoic supercontinent, whose assembly follows the earlier Columbia or Nuna configuration, and whose dispersal provides the initial conditions for subsequent continental reorganization. The rocks that formed during the assembly and breakup of Rodinia, particularly those in the Grenville and equivalent orogenic belts, and in late Neoproterozoic rift and passive margin successions, preserve the main structural, geochronological and paleomagnetic evidence used to constrain these reconstructions and to estimate the timing and duration of the Rodinia stage in the supercontinent cycle. Columbia, also widely referred to as Nuna, is a Paleoproterozoic to early Mesoproterozoic supercontinent that in many reconstructions assembles from earlier continental fragments between about 2,100 and about 1,800 million years ago, and then persists with later internal modification and marginal accretion until breakup in the interval between roughly 1,600 and 1,300 million years ago. Geological syntheses describe Columbia or Nuna as a configuration in which several major cratons that now form parts of Laurentia Baltica, the Amazonian region of South America, the West African craton, the North China and Siberian cratons, and parts of Australia and Antarctica are joined along Paleoproterozoic orogenic belts, These belts record continent-continent collision and closure of earlier ocean basins, and their ages cluster in the interval from about 2,100 to about 1,800 million years ago, consistent with a global episode of collisional assembly. In typical models, Laurentia occupies a central or near-central role with Baltica, Amazonia, and West Africa attached along one sector, and Siberia, North China, and other cratons located along different margins. Some reconstructions emphasize the nearly encircling pattern of Paleoproterozoic passive margins around Siberia, which suggests that it also forms a key element near the core of the supercontinent. The precise arrangement of these cratons remains debated, and alternative configurations are proposed that differ in the choice of neighbours and in the relative rotations applied when restoring present-day positions back through time. Paleomagnetic poles from Paleoproterozoic, igneous and sedimentary rocks on several cratons provide quantitative estimates of paleolatitude and help to discriminate among these alternatives. When poles of similar age from different continents can be brought into agreement by an appropriate reconstruction, this supports the view that those continents lie at similar latitudes and may have been joined. Some studies obtain good fits for a Columbia or Nuna configuration that places Laurentia, Baltica, and Siberia at mid to low latitudes with other cratons arranged around them, whereas other data sets favour slightly different relative positions. Because Paleoproterozoic paleomagnetic records are sparse in some regions and may include remagnetization events that complicate interpretation, the range of acceptable models is still broad compared with younger supercontinents such as Pangaea. After the initial assembly of Columbia or Nuna evidence from long-lived convergent margins and from Mesoproterozoic magmatic and accretionary belts, indicates that the supercontinent does not simply remain static. Instead, subduction zones around its edges continue to consume surrounding oceanic lithosphere, and arcs and microcontinents are accreted to its margins between about 1,800 and about 1,300 million years ago. These processes add juvenile crust and deform older margins, while overall aggregation of the main cratons is maintained. Eventually, geological and paleomagnetic indicators of rifting and new passive margins appear on several cratons in the interval between about 1,600 and 1,300 million years ago. Dike swarms, rift-related volcanic sequences, and thick clastic wedges deposited in fault-bounded basins document stretching of the lithosphere along particular sectors of the supercontinent, where extension progresses to the point of seafloor spreading new ocean basins open, and former neighbours begin to separate, marking the dispersal stage for Columbia or Nuna. The fragments produced by this breakup participate in later Mesoproterozoic and Neoproterozoic configurations, including the subsequent assembly of Rodinia. Older proposed supercontinents and continental groupings extend the record of large-scale aggregation further back into the Neo-Archean and Archean. One widely discussed example is Kenorland, a hypothetical Neo-Archean supercontinent that many models place at around 2,700 to about 2,500 million years ago. Reconstructions of Kenorland group together cratons that now form parts of Laurentia Baltica, the Kalahari region, and Western Australia on the basis of similar stratigraphic successions, shared orogenic histories and paleomagnetic data. In these models, late Neo-Archean origins such as the Kenoran or Algoman belts in North America, and comparable high-grade terrains on other cratons record collisions that build a large composite landmass, while later Paleoproterozoic rifted margins on several of the same cratons indicate subsequent breakup. Additional hypotheses propose an even earlier Archean continental assembly, known as formed around 3,100 million years ago, and consisting of parts of the Pilbara Kapval Darwa Singbum and Zimbabwe cratons. In this view, represents one of the first long-lived clusters of stable continental crust, and later acts as a nucleus within younger supercontinent configurations. Some authors prefer to describe these Archean and earliest Paleoproterozoic assemblages as supercratons, rather than full supercontinents, emphasizing that although they may include much of the continental crust present at that time, the total continental area is small compared with later epochs, and the style of tectonics in the hotter early Earth mantle may differ from that of the Proterozoic and Phanerozoic. Because the geological record for these early times is incomplete, and many cratons preserve complex overprinting by younger events, paleogeographic reconstructions of Keinorlandeur and other proposed early assemblies carry larger uncertainties than those for Columbia or Nuna and younger supercontinents. The distribution of Neo-Archean and Paleoproterozoic orogenic belts, rifted margins, stratigraphic successions and paleomagnetic poles on these cratons defines the main set of observations that any model of Columbia or Nuna and of earlier continental assemblies must satisfy. At the surface of Earth, plate tectonics is expressed through a network of plate interiors and plate boundaries that together control the creation, modification, and destruction of ocean basins. Tectonic plates consist of rigid lithosphere, including both oceanic and continental types that move as nearly coherent units over the weaker asthenosphere. Within plates, deformation is comparatively limited on geological timescales, but along plate boundaries strain is concentrated and major geological structures develop. Geologists distinguish three main classes of plate boundary based on relative motion: divergent, convergent, and transform. Divergent plate boundaries are zones where plates move apart and new lithosphere forms between them. In oceanic regions, divergence produces mid-ocean ridges, which are long continuous or segmented rises, where basaltic magma ascends from the mantle, erupts on the seafloor, and solidifies to form new oceanic crust. As cooling proceeds, the young crust moves away from the ridge axis on both sides, thickens and subsides, generating a systematic increase in seafloor depth and lithospheric thickness with distance and age. The pattern of magnetic anomalies on the seafloor, created as iron-bearing minerals in cooling lavas record the direction of Earth's magnetic field, forms symmetric stripes about many ridge axes and provides key evidence for seafloor spreading. At continental divergent boundaries, extension of the lithosphere produces rift systems marked by normal faults, crustal thinning and subsidence. Some rifts remain as failed arms that do not progress to full ocean basin opening, whereas others evolve into new oceanic spreading centers once sufficient thinning and upwelling have occurred. Convergent plate boundaries are zones where plates move toward one another. When oceanic lithosphere meets either continental or oceanic lithosphere, subduction can occur. In subduction zones, dense oceanic lithosphere bends and descends into the mantle along a dipping interface, forming deep ocean trenches at the surface and a slab that can be traced to depths of several hundred kilometers or more in seismic images. Above the subducting slab, fluids released from the downgoing plate contribute to partial melting in the overlying mantle, wedge-feeding volcanic arcs on the overriding plate. In ocean-continent convergence, these arcs are built on the continental margin and are accompanied by deformation and thickening of the adjacent crust. In ocean-ocean convergence, volcanic island arcs form on the overriding oceanic plate, and with time these arcs can collide with continents and become accreted to their margins. When convergence involves two continents whose lithosphere is too buoyant to subduct, fully collision generates wide orogenic belts with thickened crust and high mountain ranges, and the subduction of intervening oceanic lithosphere terminates. Convergent boundaries are also sites of intense seismicity, with earthquakes ranging from shallow to deep foci that trace the geometry of the subducting slab. Transform plate boundaries accommodate lateral motion between plates that slide past each other. These boundaries are dominated by strike-slip faulting, and typically lack the significant creation or destruction of lithosphere seen at divergent and convergent boundaries. Many transform faults connect offset segments of mid-ocean ridges and link them to subduction zones or other plate boundaries, forming a complex network on the ocean floor. Others lie within or adjacent to continents, where they can form long active fault zones that generate large earthquakes. Triple junctions, where three plate boundaries meet, often involve combinations of these types and may migrate or change character through time as plate motions evolve. The geometry and distribution of plate boundaries at any given time define the main ocean basins and their margins. Ocean basins initiated at divergent boundaries begin as narrow rifts that deepen and widen as seafloor spreading continues. Their shape and orientation are influenced by the pattern of rifting and by subsequent changes in spreading direction, which leave characteristic features such as fracture zones and transform offsets on the seafloor. The age structure of oceanic crust within a basin, from young rocks at the ridge axis to progressively older rocks towards subduction zones or passive margins, exerts a primary control on seafloor depth and hence on the volume of the ocean basin. In basins where oceanic lithosphere is predominantly young, average seafloor elevations are relatively shallow, whereas basins with older lithosphere are deeper. This relationship plays an important role in regulating global sea level through time. At the margins of continents, the nature of the plate boundary determines whether a margin is active or passive. Active margins coincide with convergent boundaries, where subduction or collision produces trenches, accretionary wedges, forearc basins and volcanic arcs close to the continent. Passive margins develop where a continent has rifted away from another block, and seafloor spreading has shifted the plate boundary out into the ocean. Along these margins, the transition from continental to oceanic crust is not marked by major present-day deformation, and thick sedimentary wedges accumulate on the subsiding continental shelf and slope. Many present-day passive margins, such as those along the Atlantic Ocean, record the earlier stages of continental rifting that accompanied the breakup of Pangaea. As plates continue to move, divergent, convergent, and transform boundaries interact to open some ocean basins, maintain others, and close those in which long-lived subduction has consumed most of the oceanic crust. This sequence of rifting seafloor, spreading subduction, initiation, and eventual basin closure that characterizes individual oceans is described by the Wilson cycle and operates repeatedly on different parts of the plate system, providing the surface-scale framework through which supercontinent assembly and dispersal are expressed in the arrangement of ocean basins and continental margins. Subduction, collision, and mountain building are central processes through which plates interact at convergent boundaries, and through which continents are assembled into larger units during a supercontinent cycle. In subduction zones, dense oceanic lithosphere descends into the mantle along a dipping interface beneath another plate. The geometry of this interface is defined by the distribution of earthquakes that occur from shallow depths near the trench down to several hundred kilometers beneath the overriding plate, forming a planar zone of seismicity. This pattern indicates that the subducting slab remains mechanically coherent over large depth ranges as it sinks. At the surface, subduction zones are marked by deep ocean trenches where the bending of the downgoing plate creates narrow, elongated depressions, and by volcanic arcs on the overriding plate. These arcs arise because fluids released from the subducting slab lower the melting temperature in the overlying mantle. wedge-generating magmas that ascend and feed volcanoes aligned roughly parallel to the trench. Over time, repeated intrusion and eruption build thickened crust along the arc, and sediment derived from erosion of the arc and from the incoming plate accumulates in forearc and backarc basins. In many convergent margins, pieces of oceanic crust, seamounts, island arcs and microcontinents carried toward the trench on the subducting plate are scraped off and accreted to the overriding plate instead of descending into the deep mantle. These accreted terrains are preserved as belts of deformed rocks of mixed origin and age, and their presence shows that not all arriving material follows the slab into the mantle. Through repeated accretion events, the edges of continents can grow laterally over hundreds of millions of years, producing broad composite margins composed of material from several earlier tectonic environments. Where convergence continues, an available oceanic lithosphere between major continental blocks is progressively consumed. The distance between facing continental margins decreases as the last remnants of oceanic crust subduct. The two buoyant continental lithosphere approach each other. Because continental crust is relatively thick and less dense than oceanic crust, it resists being carried into the mantle. When the remaining oceanic lithosphere is gone further, convergence must be accommodated largely by deformation of the continental margins. At this stage, a continent-continent collision begins. In such collisions, shortening of the crust occurs over broad regions. Large-scale thrust faults stack slices of crust on top of each other, producing crustal thickening. Rocks at depth experience elevated temperatures and pressures and undergo metamorphism, while partial melting can generate granitic magmas that intrude the thickened crust. The combined effect of thrusting, folding, metamorphism and magmatism builds an orogenic belt commonly referred to as a collisional origin. The thickness of the crust beneath these belts can reach 2 times or more that of normal continental crust, and isostatic adjustment causes the thickened crust to stand at high elevation, forming mountain ranges that persist for tens of millions of years until erosion and later tectonic events modify them. Orogenic belts record the history of convergence and collision in their structure and rock assemblages. In many belts, geologists observe a progression from oceanic accretionary complexes and arc-related rocks along one side through high-pressure metamorphic belts and thickened crust in the interior to less deformed sedimentary sequences on the far side, reflecting the former positions of subduction zones, collisional cores and continental forelands. Radiometric dating of igneous and metamorphic minerals in these rocks constrains the timing of deformation and metamorphism, allowing the duration of collision and the sequence of events to be reconstructed. In the context of the supercontinent cycle, long-lived systems of subduction and collision form the fundamental mechanism by which separate continents are brought together. When a large ocean basin lies between 2 major continental groups, subduction of its oceanic lithosphere along one or more margins reduces its width over hundreds of millions of years. If subduction operates preferentially on the oceanic plate that underlies the basin narrows as the plates converge. Island arcs and microcontinents that develop within the basin can be accreted to the margins of the major continents, creating intermediary crustal blocks that eventually help to form sutures between the larger plates. As convergence proceeds, the number of distinct oceanic domains separating the main continents decreases and collisions between arcs, microcontinents, and continental margins produce a series of orogenic belts that document progressive assembly. When the last major ocean between 2 large continental masses is consumed, continent-continent collision produces a final collisional orogen that welds the continents into a single larger unit. In many supercontinent reconstructions, chains of ancient orogenic belts mark these welds and can be traced today across several continents that were once contiguous. The spatial arrangement and age distribution of these belts provide key evidence used to infer the order and geometry of past collisions. Subduction does not cease immediately when a supercontinent is assembled. Instead, the new composite landmass is commonly surrounded by subduction zones, where the surrounding oceanic plates continue to descend beneath its margins. These peripheral subduction systems maintain a ring of convergent boundaries around the supercontinent and may also penetrate into its interior if smaller ocean basins persist there. Over time, continued slab descent along the margins and associated mantle flow contribute to the evolution of stress patterns within the continental interior. In some models, subduction of dense lithosphere around a large, nearly contiguous block of continents can influence the distribution of stresses and contribute to later stages of rifting and breakup, though the detailed coupling between surface convergence and subsequent extension involves additional processes treated in deeper layers of the tectonic system. Along the course of a supercontinent cycle, repeated episodes of subduction, accretion, and continent-continent collision form overlapping generations of orogenic belts. Older belts may be reactivated, overprinted, or partially removed by later events, but their remnants can preserve records of earlier cycles. Younger belts can form on or adjacent to these older structures, generating composite histories that link multiple stages of continental aggregation. The pattern of mountain belts of different ages on present-day continents is therefore a cumulative result of several cycles of subduction and collision superimposed on one another, with each major belt documenting a particular phase in the long-term assembly of a larger continental groupings. Beneath the lithospheric plates, the mantle behaves as a very slowly flowing solid that transports heat from the deep interior toward the surface through convection. The mantle is composed mainly of silicate minerals that are strong on short timescales but can deform viscously over millions of years under differential stress and high temperature. Temperature within the mantle increases with depth, from values of order 1000 degrees Celsius in the upper regions to values above 3000 degrees Celsius near the core mantle boundary. Heat that drives convection comes from several sources, including residual heat from planetary accretion and differentiation, and heat produced by the decay of radioactive isotopes distributed through mantle and crustal rocks. The efficiency with which this heat is transported upward depends on the viscosity structure of the mantle, the temperature contrast between deep and shallow regions, and the geometry of thermal boundary layers at the top and bottom. In fluid mechanics, terms convection in the mantle is often characterized by a Rayleigh number, a dimensionless quantity that measures the tendency for buoyancy-driven flow relative to viscous resistance and thermal diffusion. For plausible viscosity and temperature contrast, estimated Rayleigh numbers for Earth's mantle exceed by large factors the critical value above which convection develops. Under these conditions, heat transport is dominated by organized patterns of rising and sinking mantle rather than by conduction alone. In broad outline, cold, dense lithosphere that has been cooled at the surface and thickened with age forms the upper thermal boundary layer of the convecting system. Where this boundary layer fails and sinks at subduction zones, slabs of lithosphere penetrate into the mantle and descend toward the core mantle boundary. At depth, the descending slabs form prominent high-velocity structures in seismic tomography images, indicating regions where seismic waves travel faster than in the surrounding mantle. These slab-related anomalies can in many cases be traced from the surface down through the transition zone and into the lower mantle, suggesting that sinking lithosphere traverses much of the mantle thickness. At the base of the mantle, near the core mantle boundary, low-velocity zones are observed in seismic models. Among the most prominent of these are the large low-shear velocity provinces beneath Africa and beneath the central Pacific. These regions extend laterally for thousands of kilometers and rise hundreds to perhaps over 1,000 kilometers above the core mantle boundary. They are characterized by reduced seismic wave speeds relative to the average lower mantle, and several lines of evidence suggest that they represent hot, possibly compositionally distinct thermochemical piles rather than purely thermal anomalies. Many numerical models of whole mantle convection that assimilate plate motion histories show that subducted slabs tend to accumulate around and partly beneath the margins of such deep, low velocity structures, forming so-called slab graveyards at the base of the mantle. In these models, the distribution of cold downwellings and hot upwellings interacts with any dense basal layer to produce a convection pattern that has a small number of long wavelength cells on the scale of the entire mantle. The geometrical pattern obtained in such models with two major antipodal hot regions and surrounding belts of cold material resembles the degree 2 structure inferred from seismic tomography of the lowermost mantle in which the African and Pacific large, low-shear velocity provinces occupy roughly opposite sectors. Rising mantle associated with these basal structures can give rise to broad upwellings and narrower mantle plumes. Mantle plumes are columns or conduits of anomalously hot material that ascend from deep levels, possibly from near the margins or tops of the basal thermochemical piles. As they rise, decompression can cause partial melting, and the resulting magmas feed intraplate volcanic regions at the surface, including some ocean island chains and large igneous provinces. The spacing thickness and longevity of plumes in geodynamic models depend on the viscosity structure of the mantle, the thermal contrast across the core mantle boundary, and the presence of dense basal layers. In models with thermochemical piles, plumes tend to originate preferentially from their edges or tops, reflecting the combined influence of heat flux from the core and the focusing effect of surrounding cold slabs. At the same time, the upper mantle and transition zone host additional upwellings and downwellings connected to variations in lithospheric age subduction geometry and local mantle properties, so convection involves a spectrum of scales from global to regional. The large-scale pattern of mantle flow is constrained not only by seismic tomography, but also by observations of Earth's gravity field, the long-wavelength geoid, and the dynamic topography of the surface and seafloor. Long-wavelength geoid anomalies correlate with major lower mantle structures, and numerical models indicate that these anomalies arise in part from density contrasts associated with cold slabs and hot upwellings deep in the mantle. Dynamic topography, which represents surface elevation, supported by viscous flow in the mantle rather than by crustal thickness. Variations alone is influenced by these flow patterns. Regions underlain by upwelling mantle tend to be uplifted relative to surrounding areas, whereas regions above downwellings may be depressed. This dynamic contribution is superimposed on the effects of crustal isostasy and local tectonics, and can change slowly over tens of millions of years as mantle flow reorganizes. The coupling between mantle convection and surface plates occurs through mechanical tractions at the base of the lithosphere and through the integrated buoyancy and strength contrasts of plates and slabs. In many geodynamic models, sinking slabs at subduction zones provide a major contribution to the driving forces of plate motions, a mechanism often referred to as slab pull. Dense slabs that penetrate into the lower mantle can exert significant negative buoyancy forces that help to draw plates towards subduction zones. At the same time, tractions from large-scale mantle flow acting on the base of plates can influence plate velocities and directions, especially for plates that lack major attached slabs. Ridge push from elevated mid-ocean ridges and resistive forces at faults and plate boundaries also contribute. The relative importance of these forces varies among plates and over time, but in a global view, plate motions and mantle convection form a coupled system in which surface plates both respond to and help organize flow in the underlying mantle. Over long intervals of hundreds of millions of years, numerical simulations and plate reconstructions suggest that large-scale mantle convection exhibits persistent patterns with stable or slowly drifting zones of upwelling and downwelling, and with slab material accumulating in preferred regions near the base of the mantle. These patterns define the background flow field within which plates move and interact, and set the thermal and mechanical conditions in the mantle beneath ocean basins and continents on the timescales relevant to the supercontinent cycle. Links between mantle flow and supercontinent behavior are investigated by combining seismic images of the deep mantle models of whole mantle convection and reconstructions of plate motions and large igneous provinces. Seismic tomography reveals that the lowermost mantle contains two large low shear velocity provinces beneath Africa and beneath the central Pacific. These structures extend laterally for thousands of kilometers and rise hundreds to more than 1,000 kilometers above the core mantle boundary, and their reduced shear wave speeds relative to the surrounding mantle indicate that they are hotter or compositionally distinct or both. Tomographic models show that subducted slabs which appear as high-velocity anomalies tend to accumulate in belts around the margins of these low-velocity regions, rather than passing directly through them, suggesting that the large low-shear velocity provinces act as long-lived thermochemical piles that interact with descending lithosphere. The edges of these piles are inferred in many studies to be preferred sites for mantle plume initiation. When these edges are mapped in the lowermost mantle, and compared with the reconstructed positions of large igneous provinces and intraplate volcanic provinces at the surface, over the past several 100 million years, many reconstructions place large igneous provinces above or near the projected margins of the low shear velocity provinces at the time of eruption. This spatial correlation supports the idea that plume generation zones lie preferentially along the edges of the African and Pacific low shear velocity provinces, and that these zones have remained in broadly similar positions in the deep mantle over at least the past 200 to 300 million years. Kimberlite fields and other deep-sourced magmas also show clustering above these margins in several studies, further linking long-lived basal mantle structures to focused upwelling and plume activity at the surface. Supercontinent reconstructions are increasingly compared against this deep mantle framework. In some models, past supercontinents such as Pangaea are positioned so that their interiors lie above or near the present African low-shear velocity province and its ancestral structures, while major subduction zones encircle the supercontinent and lie above regions where slabs later form cold belts around the margins of the basal piles. In this configuration, a supercontinent is surrounded by a nearly continuous ring of subduction that delivers cold lithosphere to the lowermost mantle and defines a circum-supercontinent subduction girdle. Numerical models of whole mantle convection, driven by such subduction patterns, show that return flow from sinking slabs can reorganize the convection pattern beneath the supercontinent. In several simulations, an initially asymmetric pattern dominated by a single hemispheric downwelling evolves into a pattern with two antipodal upwellings separated by a girdle of downwellings, a geometry often described as degree 2 convection. In these models, a broad upwelling develops beneath or near the supercontinent, and narrower plumes may rise from the margins of the basal thermochemical piles that accompany this upwelling. The onset of strong upwelling and plume activity near the base of the supercontinent contributes to elevated heat flux and mechanical weakening of the lithosphere, particularly where upwellings intersect regions of pre-existing lithospheric thinning or inherited rift structures. Some geodynamic studies find that such focused basal heating and associated dynamic topography can increase extensional stresses in parts of the supercontinent interior and along particular margins, favoring the initiation of rifting that may eventually progress to breakup. In this view, the same mantle circulation that drives the long phase of subduction and continental assembly also sets the conditions for supercontinent dispersal by reorganizing flow beneath the assembled landmass. Other classes of models explore how the presence, thickness, and density contrast of a basal thermochemical layer influence the stability and mobility of large, low-shear velocity provinces and the regularity of supercontinent cycles. In simulations where basal piles are relatively stable and remain near fixed positions for long intervals, continents move above a quasi-stationary deep mantle reference frame. Supercontinents tend to assemble in preferred longitude bands above or near the upwelling regions associated with the basal piles, and superplumes rising from their margins repeatedly interact with continental lithosphere during successive cycles. In alternative simulations, basal structures are more mobile and can be reorganized by cumulative slab influx over time, leading to shifts in the locations of major upwellings and in the long wavelength pattern of convection. These differences affect how strongly supercontinent locations are tied to specific deep mantle features and influence the degree to which the supercontinent cycle can be described as operating with a single characteristic period. Idealized convection models with simple continents and heating modes often produce cyclic aggregation and dispersal with intervals of about 400 million years when plumes are moderate in strength, whereas the introduction of strong plumes or changes in basal layer properties can disrupt a regular rhythm and generate more variable cycle lengths. Geological observations provide independent test for these models. The timing of large igneous provinces relative to known or inferred supercontinent stages, the clustering of plume-related magmatism in particular time windows, and the correlation of reconstructed large igneous province sites with projected plume generation zones at the edges of low shear velocity. Provinces are used to evaluate whether deep mantle upwellings are systematically linked to supercontinent breakup and to the assembly path of subsequent configurations. Isotopic studies of mantle-derived rocks also investigate whether the composition of upwelling mantle beneath supercontinents and along their margins changes in step with the assembly and dispersal of supercontinents, and with the growth and erosion of superoceans as would be expected if subducted material accumulates and is later sampled by plumes in a supercontinent-coupled circulation cycle. Although many of these indicators support a coupling between long-term mantle structure and the supercontinent cycle, significant uncertainties remain regarding the exact mobility of the low shear velocity provinces, the persistence of specific plume generation zones over billions of years, and the way in which changes in mantle rheology, internal heating, and plate strength over Earth history might have altered the strength and periodicity of supercontinent cycling. Paleomagnetism studies the remanent magnetization preserved in rocks to infer the direction and intensity of Earth's magnetic field at the time the rocks acquire their magnetization. In most paleomagnetic applications to tectonics and supercontinents, the working assumption is that over long intervals the time-average geomagnetic field is well approximated by a geocentric axial dipole aligned with the rotation axis. under this assumption, the inclination and declination of magnetization directions measured in suitable rock units can be converted into the position of a paleomagnetic pole and into the paleolatitude and orientation of the rock body at the time of magnetization. When many measurements from a single tectonic block or craton are combined, they define a mean paleomagnetic pole for that block at a particular geological age. A sequence of such poles arranged in time order defines an apparent polar wander path for that block. The apparent polar wander path is the locus of paleomagnetic pole positions that would be observed if the block is held fixed in its present position, while the pole is allowed to move on a globe. Because the actual motion involves movement of the block relative to a geomagnetic field that stays roughly aligned with the rotation axis, this path mainly records the drift of the block across the globe, with possible contributions from true polar wander, where the entire solid Earth reorients relative to the rotation axis. Apparent polar wander paths are constructed for individual continents or cratons by compiling paleomagnetic poles that pass reliability criteria. Such criteria typically require adequate numbers of independently oriented samples, acceptable statistical precision on mean directions, age control that links magnetization to rock formation or deformation, and field tests such as fold or conglomerate tests that confirm the magnetization is primary or has a known relative age. Paleomagnetic poles that satisfy these standards are assembled into reference paths that describe the motion of each block through time. For example, long apparent polar wander paths have been compiled for Laurentia Baltica, Siberia, and other cratons over large parts of Proterozoic and Phanerozoic time, and these paths are routinely updated as new data become available. In supercontinent reconstructions, these paths provide quantitative constraints on where and how blocks can be positioned relative to one another at given ages. If two continents share a common path segment when reconstructed into contact, this indicates that they have moved together as part of the same plate or rigid group during that interval. If paths from different blocks do not match under a proposed reconstruction, then the reconstruction is inconsistent with the paleomagnetic data. Paleomagnetic data are used to test proposed fits based on geological matching of margins, orogenic belts, and stratigraphic successions against independent directional information. For supercontinents such as Pangaea, paleomagnetic tests were historically used to distinguish between alternative fits of the continents, such as different relative rotations between North America and Europe. More recently, paleomagnetic data have been central in evaluating competing arrangements of cratons in Rodinia and Columbia or Nuna. In these older intervals where marine magnetic anomaly data are unavailable, and passive margin histories are sometimes incomplete, paleomagnetism provides some of the few quantitative constraints on continental positions, because paleomagnetic poles constrain latitude and orientation but not absolute longitude, and because the sense of polarity can be reversed without changing the fit, there remains a family of longitudinally shifted configurations that are all compatible with a given set of poles. To reduce these degrees of freedom, paleomagnetic information is combined with geological indicators such as matching, orogenic belts, sediment provenance patterns, faunal provinces, and the distribution of rifted margins and passive margin sequences. In addition, some studies use hotspot track geometries, slab sinking reconstructions, or assumptions about the positions of long-lived deep mantle structures to place further limits on permissible longitudes. True polar wander, in which the entire solid Earth rotates relative to the rotation axis, also influences apparent polar wander paths. Separating the contributions of plate motion and true polar wander requires comparing paths from multiple continents, and searching for intervals where poles from all well-constrained blocks move in a similar fashion relative to the present rotation axis. In such intervals, part of the apparent motion may reflect reorientation of the whole planet, rather than relative plate motion alone. Paleomagnetic data sets must therefore be evaluated for possible true polar wander signals, remagnetization events that reset the magnetic record at younger times, inclination shallowing in sediments and structural complexities that rotate blocks after magnetization. These factors contribute to the uncertainties in constructing apparent polar wander paths and in deriving plate reconstructions. Paleomagnetism is one of the few methods that directly record past directions of the geomagnetic field in rocks of many ages, and provides a way to quantify past plate motions on spherical geometry for the supercontinent cycle sequences of paleomagnetic poles when combined into apparent polar wander paths for major cratons, are used to estimate when continents move together, when they separate, and how they rotate relative to one another over intervals of hundreds of millions of years, providing constraints on the geometry and timing of supercontinent assembly and dispersal. Geochronology uses the decay of radioactive isotopes to measure the ages of rocks and minerals, and to place tectonic events such as rifting, subduction, collision, and magmatism into a quantitative time framework. In the context of the supercontinent cycle, radiometric dating methods are applied to igneous metamorphic and sedimentary rocks in collisional belts, rifted margins, passive margins, and large igneous provinces to determine when continents collide, when oceans open, and when major magmatic pulses occur. Among the available systems, uranium lead dating of zircon is one of the most widely used for constraining the timing of magmatic and high-grade metamorphic events, because zircon incorporates uranium but little lead. When it crystallizes, has high closure temperatures and can survive multiple geological cycles while retaining older age domains. UPB ages from zircon in granitoid plutons, volcanic rocks, and high-grade metamorphic rocks in orogenic belts define the emplacement and metamorphic histories of these belts. By sampling plutons that intrude collisional structures, geochronologists can date the late stages of crustal thickening and magmatic addition. By dating metamorphic zircon overgrowths, or metamorphic minerals that host zircon inclusions, they can constrain the timing of peak metamorphism. In many well-studied belts, such as those associated with the Grenville origin, the Pan-African system or Paleozoic collisional belts around Pangaea, dense sets of zircon UPB ages define limited time intervals for major collisional episodes and associated magmatism, helping to bracket the assembly stages of supercontinents. High-precision techniques using isotope dilution, thermal ionization mass spectrometry, or sensitive high-resolution ion microprobes allow age uncertainties to be reduced to less than 1 million years in favorable cases, which is sufficient to resolve the sequence of intrusive metamorphic and deformational events within single origins over total durations of several tens of millions of years. Other radiometric systems complement zircon UPB chronometers, argon-argon dating on mica amphibolae, and feldspar records cooling through specific temperature windows, and can constrain when thickened crust begins to cool after collision, or when exhumation brings rocks toward the surface. Rubidium, strontium, samarium, neodymium, and lutetium, hafnium systems in whole rocks and minerals can provide both ages and information about the sources of magmas. In large igneous provinces and dike swarms associated with rifting, and break up UPB dating of zircon and baddelite in mafic dikes, and sills, constrains the onset, peak, and duration of magmatic events that often coincide with early stages of continental separation. For example, mafic dike swarms that cut older crust and radiate from inferred plume centers can be dated precisely and correlated across now separated continents, showing that rifting and flood basalt volcanism occurred synchronously along the margins of supercontinents during their breakup phases. Detrital zircon geochronology extends the reach of UPB dating into sedimentary successions. Sandstones and other clastic rocks contain zircon grains sourced from multiple upstream regions, each preserving a crystallization age that reflects magmatic events in its source area. Large compilations of detrital zircon ages from many sedimentary basins reveal global age distributions with prominent peaks at several times in Earth history, commonly near 2,700 and 1,900 and 1,600 and 300 million years. These peaks are interpreted as times when large volumes of zircon-bearing felsic magmas were generated and preserved, often during supercontinent assembly in major collisional origins. By comparing age spectra from basins on different continents, geologists can test whether they share common provenance, and hence were once connected parts of larger land masses. In some cases, changes in the dominant age populations in detrital zircon suites through time record shifts from one supercontinent configuration to another as erosion from older origins declines and new magmatic belts develop during later assemblies. Radiogenic isotope systems such as samarium, neodymium and lutetium hafnium provide additional information about crustal growth and reworking across supercontinent cycles. The samarium-neodymium system is used to calculate depleted mantle model ages and epsilon neodymium values that indicate whether a given rock or sediment was derived from relatively juvenile crust, newly extracted from the mantle, or from older continental material recycled during later events. The lutetium hafnium system in zircon is especially useful because hafnium isotopes in zircon can record the time at which the magma's source separated from the mantle, even when the zircon crystallization age is younger. By plotting hafnium isotopic compositions against zircon UPB ages, studies compile trajectories of juvenile and evolved magmatism through time. In many such compilations, positive hafnium isotope values and young model ages cluster near times of supercontinent assembly, suggesting enhanced addition of new juvenile crust during collisional origins, whereas more evolved values dominate during times of supercontinent breakup, when reworking of existing crust in extensional settings is more prominent. These trends have been described for multiple cratons and for specific regions such as the Precambrian belts of Asia and the Mongolian orogenic systems, and they form one of the main lines of isotope evidence connecting deep, crustal processes to the supercontinent cycle. Strontium, neodymium, lead, and osmium isotopes in basalts. Large igneous provinces and alkaline complexes provide geochemical traces of mantle sources and of interactions between plumes, lithosphere and asthenosphere during rifting and breakup. For example, combined SRAN PB isotope signatures in flood basalts and associated magmatic rocks are used to distinguish melts derived from depleted upper mantle from enriched plume sources rooted in deep mantle structures, and from lithospheric mantle modified by prior subduction. In some large igneous provinces that coincide in time with supercontinent breakup isotope data, support contributions from both deep mantle plumes and continental lithosphere, implying mixing between plume-derived melts and the base of thick continental keels. Osmium isotopes in some mafic and ultramafic rocks also record contributions from ancient lithospheric mantle versus more juvenile asthenospheric sources. These isotopic distinctions help evaluate whether major magmatic events are primarily related to plume upwellings, to edge-driven convection and decompression beneath rifted margins, or to a combination of processes, and whether they tap mantle domains that may have been influenced by long-term slab accumulation beneath former supercontinents. Geochronology and isotope geochemistry are closely linked in provenance studies that trace sediment pathways and link basins on different continents to shared source regions. Detrital zircon UPB ages combined with hafnium isotopes and whole rock samarium neodymium data allow reconstructions of when and where crustal material was generated, how long it resided in the crust before erosion, and how it was transported across changing continental configurations. In collisional belts and accretionary margins, age and isotope patterns of igneous rocks, metamorphic rocks and sediments can be used to distinguish external accretion of juvenile arcs from internal reworking of older continental crust. Over long intervals, compilations of such data reveal shifts between periods dominated by creation and preservation of juvenile crust in external origins, often during assembly, and periods dominated by reworking and recycling during breakup and dispersal. In this way, radiometric ages and isotope ratios in rocks and minerals document not only the absolute timing of rifting collision magmatism and sedimentation, but also the changing balance between crustal growth and crustal reworking through successive episodes of supercontinent assembly and fragmentation. And they provide an independent set of constraints on the sequence and character of events, inferred from structural geology, paleomagnetism, and plate reconstructions. Reconstructing the supercontinent cycle relies on combining several independent categories of observation into kinematic models that respect geological, geophysical, and geochemical constraints. Field-based geology provides direct evidence of past plate interactions in the form of orogenic belts, sutures, accretionary prisms, passive margins, rift systems, and sedimentary basins. Mapping of structural trends, metamorphic grades, and magmatic provinces across multiple continents allows correlations to be made between belts that are now far apart but that once lie side by side. When a collisional belt of a particular age and character can be traced from one continent into another, or when matching passive margin sequences of similar age and stratigraphy are found on opposing continental edges, these correlations define candidate join positions for past configurations. Paleomagnetism contributes quantitative information on paleolatitude and orientation for each craton at different times. Apparent polar wander paths constructed for individual continents are used to test whether geological fits are consistent with a common motion history during supercontinent stages and to identify intervals where blocks must have moved independently. Geochronology provides the temporal framework in which these spatial relationships are placed. Radiometric ages from igneous and metamorphic rocks in orogenic belts constrain the timing of collisions, while ages from rift-related magmas and passive margin successions bracket the onset of extension and seafloor spreading during breakup. Detrital zircon age spectra and isotope signatures in sediments reveal provenance changes that accompany shifts from one configuration to another. Geochemical and isotopic studies of mantle-derived rocks and large igneous provinces help to distinguish between plume-related magmatism and melts, derived mainly from lithospheric or asthenospheric sources, adding information on how mantle domains are sampled during assembly and dispersal. For younger parts of the record, marine magnetic anomalies on the seafloor and fracture zone patterns provide detailed constraints on spreading rates and directions, allowing plate kinematic models to be built with relatively high temporal resolution for the breakup of Pangaea and the evolution of present-day ocean basins. For older intervals where oceanic crust has been recycled into the mantle, reconstructions depend more heavily on continental geology, paleomagnetism and geochronology, and so carry larger uncertainties. Integrating these diverse datasets requires iterative plate modeling, in which proposed continental fits and plate circuits are tested against all available constraints and adjusted when conflicts are found. Global plate reconstruction models spanning several 100 million years of Earth history compile plate boundaries, relative and absolute plate motions, and paleogeographic grids in a way that attempts to satisfy the combined requirements from structural geology, paleomagnetism, stratigraphy, and mantle imaging. When different research groups use different weighting schemes for conflicting data, or make different choices about how to treat poorly constrained poles, remagnetization, or ambiguous correlations, they may arrive at alternative supercontinent models that all reproduce some but not all observations. Major uncertainties in the supercontinent cycle therefore arise from both limitations in the data and from methodological choices. Paleomagnetic coverage is uneven in age and space, and some key intervals lack reliable poles for several cratons. Remagnetization inclination, shallowing, and structural rotation can affect older rocks and require careful tests before directions are accepted. In many regions, orogenic belts have been reworked by later events and original sutures or passive margin geometries are obscured. Radiometric age data are dense in some belts and sparse in others, and different decay systems may record different stages in the same tectonic event. Reconstructions of Rodinia, Columbia, or Nuna, and proposed earlier assemblies illustrate these challenges as published models differ in the number and sequence of collisions in the relative positions of particular cratons and in the length of time for which a coherent supercontinent exists. There is also no single agreed definition of what fraction of continental crust must be joined to qualify as a supercontinent, or how to distinguish a large superterrane such as Gondwana from a global-scale configuration such as Pangaea. So different authors may count different numbers of supercontinents in Earth history. Additional uncertainties concern the regularity of the supercontinent cycle and its coupling to deep mantle structure. Estimates of cycle length, based on the timing of Rodinia, Pangaea, Gondwana, and Pangaea yield intervals of roughly 300 to 500 million years, but the scatter in assembly and breakup ages and the possibility of overlapping or partial cycles make it difficult to assign a single period. How stable the African and Pacific large low-shear velocity provinces have been over billions of years, how strongly they control preferred assembly locations, and how their internal evolution may have changed with secular cooling of the mantle remain open questions. The style of plate tectonics itself may have varied in the Archean and early Proterozoic, affecting how directly early continental clusters can be compared with younger supercontinents. Because no oceanic lithosphere older than about 200 million years is preserved at the surface, reconstructions for most of Earth history must be inferred indirectly from continental records and from deep mantle images. As a result, the supercontinent cycle is characterized by well-constrained stages in the most recent few 100 million years, progressively larger uncertainties for earlier Proterozoic configurations, and broad but more speculative outlines for Neo-Archean and Archean assemblies. In all cases, proposed models are expected to remain provisional and subject to revision as new paleomagnetic measurements, geochronological data, field correlations, and mantle imaging results become available, and comparisons among alternative reconstructions focus on how effectively each satisfies the existing multidisciplinary observational constraints.